Hi, I am Sanjay Patel. Today we are going to discuss an important concept in the ring theory, and that is the concept of characteristic of a ring. So first, let me write down the definition and then I will explain the meaning of characteristic. So let R plus dot be a ring. R plus dot be a ring. Okay. And suppose or let me write directly, let R plus dot be a ring, and if there exists a smallest positive integer, if there exists a smallest positive integer, remember that there may or may not exist. If there exists smallest positive integer n, okay, such that n times a equal to 0 element for every element a in the ring R, then the number n is known as the characteristic. It is known as characteristic of the ring R. Okay, and we denote it by the symbol. It is denoted by the symbol CHAR. Characteristic of R is equal to n. Okay, so this is the notation for the characteristic of the ring. Now let us understand the meaning of all these things. R is a ring. It is any ring. Okay, if there exists a smallest positive integer n such that n into a equal to 0, means if you add a n times, then you must get 0, and that must be true for every element a belongs to R. Remember, this n is a positive integer, a is an element of the ring. Okay, so this is not a simple multiplication of numbers. It is a multiplication of an element of a ring. That ring can be any ring. It can be ring of matrices. So if say A is a matrix like this, 1 0 2 1, okay, then n into A, that is 3 into A, you know the meaning of 3 times this matrix. That means you have to multiply all the numbers in this matrix by 3. Or you can, in other words, you have to add the matrix A with itself, say 3 times. So that is the meaning here. Another way of looking at this definition in a simple way is from your group theory knowledge. So let me just remind you about that group theory concept of order of an element. If G is a group with respect to some binary operation, say star, if this is a group, okay, and suppose E is the identity element of the group, and for an element A belongs to the group G, if there exists the smallest positive integer such that a raised to n is equal to e, then we know that this n is called order of the element A, and we are denoting this symbolically by the notation O into bracket A is equal to n. That means order of A is equal to n. Here in the case of group theory, you know the meaning of A raised to n is again A star. There is only one operation in the group, so it is something like this: A star A. How many times? N times. Remember this. And if the operation star, because G can be any group, star can be any operation. So if the operation star is say plus, that is operation of addition, any kind of addition, then this notation a raised to n, that is a plus a n times, it becomes this thing. And that is the case in our ring theory. This we are denoting by n times a, and this must be say identity element, but whenever an operation is plus, the identity element we write as 0. So combining all this, in short, na equal to 0, na equal to 0 means the additive order of the element a is n. So characteristic of a ring is nothing but that additive order of every element is n. Okay, then if such a smallest number n exists, then that smallest number n is called the characteristic of the ring R. Okay, let us understand more concretely by taking one particular example. So let me take a simple example. Consider the ring of say residue classes modulo 6. Let me take Z6 plus 6 and dot 6. You know what is a Z6? Z6 contains these residue classes, class 0, class 1, class 2, and so on up to class 5. Okay, so there are 6 elements in this, and the operation plus 6 means addition modulo 6 and dot 6 means multiplication modulo 6. That you know very well. Okay, we want to find the characteristic of this ring. Fine. So that means I want to find some positive integer n such that n into a is equal to 0 for every a belongs to the ring R, which is Z6. Okay, so that means what should I do here is I must look at this thing. Okay, n into a is equal to say 0. This 0 is class 0. Remember, this a and this 0 both are elements of the ring. Okay, so we want to find such a smallest number so that this is true for every a belongs to class A belongs to Z6. Let me begin with some particular value. So let us consider the element class 2. If I take say a is equal to class 2 belongs to Z6, then let me keep on adding 2 with itself. Say class 2 plus 6 class 2 is equal to class 4, and this in our notation, you know, it is denoted by 2 times class 2. Okay, this 2 is integer, this 2 is the class 2 is the element of the ring. So it is something like 2 into a, that is a plus a, and finally you are getting this new value. Okay, just it is for your understanding. So what we are getting here is 2 times a is equal to 4, and this is not equal to class 0, that is 0 element of the unit ring. So this is not fine. So let me go further. Let me take 3 times class 2, that is class 2 plus class 2, how many times? 3 times. Okay, you know how to add all this. You can add one by one, means by taking pair, or you can add all the numbers together. Say 2 plus 2 plus 2, that is 6, and 6 is same as class 0. So we are getting 0 here. So what I have proved here is 3 times class 2 is equal to the element 0. So that is my one observation. Okay, for one element class 2 belongs to Z6, I am getting 3 into that element class 2 is equal to 0. But this 3 may not work for the other elements. Let me take now, say a is equal to class 1 belongs to Z6. Then how many times I should add 1 with itself to get 0? Means how many times I should continue this process Okay, so final answer is 0. How many times? So that will be the answer for your that number n. How many times that class 1 should be added with itself. And this plus is actually our addition modulus 6 operation that is understood. So if I take 1 plus 1, that is class 1 plus class 1, or in other words 2 times 1, it is 2. So it is not 0. Okay, it is not equal to 0 element. If I take 3 times 1, that is 1 plus 1 plus 1, so 3, it is again not 0. If you continue like this, you can understand that the only point at which we are getting 0 is adding the class 1 with itself 6 times, because 1 plus 1 plus 1 plus 1 6 times gives you class 6, and class 6 is same as class 0, because when you divide 6 by 6, the remainder is 0. So this is the 0 element. Okay, so that is 6 times class 1 is equal to 0. This 6 is integer, and this class 1 is an element of the ring R. Okay, so in this case what we have proved is 6 times class 1 is equal to 0. Here I have put that 3 times class 2 is equal to 0. So what we want to do is we want to try different, we want to check for all the elements in this ring and see that what is the smallest element, or what is the smallest positive integer n for which n times all the elements gives you 0. Okay. So 3 into, so 6 is the smallest number in this case we are getting. Let me try for other values also. If I take 3, the number 3, class 3 belongs to Z6, then can you give me what is n, so that n times class 3 is equal to class 0, that is the 0 element. Then it is very simple, that just adding 3 with itself 2 times, say 2 into 3, that is 3 plus 3 2 times, and 3 plus 3 means 6, and 6 is equal to 0, so we are through. In this case, order of class 3 is 2. Okay, additive order of class 3 is 2. So this is also not fine. Now, if you keep on adding 3 with itself 6 times, definitely you will get 0. Okay. What about 4? For the element class 4 belongs to Z6, what is n, so that n into class 4 is equal to 0. Okay, so that gives you 4 plus 4 8, so that is not working. But if I add 4 with itself 3 times, the 3 times 4 is 4 plus 4 plus 4, that is 12, and 12 is equal to 0. So in this case, our additive order of 4 is 3. So if you observe all this, then you can realize that 6 is the smallest number. 6 is the smallest number. This is the smallest positive integer, such that 6 times a equal to 0 for every a belongs to Z6. Let us verify this for all the elements. 6 times a means, 6 times a means 6 into, say, class A is equal to class 0. So in that sense we are talking. You take all the elements from the ring Z6. Say 0 if you add 6 times, you will get 0. Class 1 if you add 6 times, that we have wrote is 0. 2 if you add 6 times, 2 plus 2 plus 2 plus 2, so that is 6 times gives you 12, and 12 equals 0. 3 if you add 6 times, 3 plus 3 plus 3 plus 3, 6 times gives you 18, and 18 is congruent to 0 mod 6. So this you can verify for all the elements. If you keep on adding with itself, say 6 times, then you'll always get 0, and 6 is the minimum positive integer, or the smallest positive integer for which it works for, say, all the elements of the ring. In short, for 6, we have 6 into a equals 0 for every a in the given ring. Therefore, I can say the characteristic of the ring Z6 is equal to 6. Okay, characteristic of Z6 is equal to 6. Remember, in definition we have written of characteristic that if there exists a smallest positive integer n such that n equal to 0 for every a belongs to R, then n is called characteristic of the ring R. But if such a number n does not exist, then we say that the characteristic of the ring is infinite or 0. So let me mention that as an independent definition. Let me write this way. If there does not exist n belongs to n such that n into a equal to 0 for every a belongs to the ring R in the above definition, then R is said to be, or R is said to have infinite, is said to have infinite or 0 characteristic, infinite or 0 characteristic. So we write characteristic of R equal to 0 or infinity. Okay. Now, immediately some question can arise, in which ring this kind of thing happens, and it is very simple, and that ring is nothing but our famous ring of integers. If I take the ring of integers, say if I consider the ring of integers z plus dot, where plus and dot are our usual addition and multiplication of integers, then in this ring, if you take for example, say if I take a is equal to 2 belongs to z, and if I keep on adding 2 with itself, then I will never get 0. So there is no n belongs to the set of natural numbers, so that n times 2 equal to, say, the integer 0, because 0 element in this ring is the integer 0. Okay, and this means, is 2 plus 2 plus 2 n times. So if you keep on adding 2, it keeps on increasing. You will get a bigger and bigger integer. So it will never become 0. So we cannot find such an n in the ring of integers. I can say the characteristic of z is 0 or infinite. So characteristic of the ring z is equal to 0. So we have seen one example of a ring with finite characteristic and one example of a ring with infinite characteristic. Okay, and there is nothing special about this Z6. You can take any ring of the type Zn and you can show that characteristic of Zn is always n. Okay, so from the definition of characteristic, you must have realized that the condition that n into a equal to 0 for a characteristic, one has to check for every a belongs to R. Okay, and that is very difficult when the ring R has infinitely many elements or many elements. So there must be some nice way or a easy way to find the characteristic. Okay, but before I explain you those things that I will definitely do in the next lecture, but before I explain or prove that result, let me give some one or two more examples. Say characteristic of Z is 0. Same way you can prove that characteristic of the ring of real numbers. I will simply write 0. Characteristic of the ring of complex numbers is 0. Characteristic of the ring of matrices, 2 cross 2 matrices with real entries, is equal to 0. Remember, if you take any matrix, then it is not always possible to find n, so that n times the matrix A is equal to the 0 matrix. Okay, means it is fine in this case. But if I consider this another interesting example, say consider the ring R is equal to the set of all matrices A, B, C, D, okay, where A, B, C, D belongs to the ring Z2, which is equal to say class 0 and class 1. But I will write this class 0 and class 1 for simplicity as say only 0 and 1. Okay. So this R we have already mentioned in our earlier videos that this R is, I can also write this way, it is M2 cross 2 with entries in Z2. So this R has 16 elements and this R is a ring, okay, with respect to matrix addition and matrix multiplication. This is a ring. And we are interested in finding the characteristic of this ring. What is the zero element here? The zero element in this ring is the zero matrix, which is obviously there in R. This is the zero element. Okay. Now if I take one element, say A, something like this, 1, 1, 0, 0. You know, this belongs to our ring R. A, B, C, D, you can take either 0 or 1. So there are 4 places A, B, C, D, and each of this can be filled up by these two symbols 0 and 1. So we have 2 into 2 into 2 into 2, that is 4 times 2 into 2, and that is 2 raised to 4, means there are 16 possible matrices. I am taking one of the matrix from the set R. Now if I take A plus A, that is 2 times A, that is A plus A, what I will get is 1, 1, 0, 0 plus 1, 1, 0, 0. And by adding these two, 1 plus 1 is equal to 2, but 2 is equal to 0. Again 1 plus 1 is equal to 2 and 2 modulo 2 is 0. 0 plus 0 is 0, 0 plus 0 is 0. So we are getting 0 here. So in this case, we have 2 times A equal to say the 0 element. And not only for this particular matrix that we are getting 2 into A equal to 0, but we can show that, or we can verify. We can verify that 2 into say every matrix say X equal to 0 for every matrix X in the ring R. So I can say the characteristic of this special ring is 2. Characteristic of the special ring is 2. Okay. So this is another interesting example. One more interesting example before we say stop here. Let me mention that problem. If R is a Boolean ring, then prove that characteristic of R, prove that the characteristic of a Boolean ring is always 2. And there is nothing to prove actually, because we have already done this result in our previous video. We have already proved that in the Boolean ring, we know that in the Boolean ring, say A plus A equal to 0 for every A belongs to R. So this is to be proved if this question is asked. And A plus A means 2 times A equal to 0 for every A belongs to R. So I can say 2 is the smallest number for which 2 into A equal to 0 for every A. So characteristic of the Boolean ring is also 2 in this case. So another important example about the characteristic. Okay. So in the next lecture, we'll be proving some theorems about the characteristic of a ring and show you how to find the characteristic of a ring in an easy way when the ring has the unity element. We don't have to look at all the elements in the ring. Just concentrate on the unity element and you can determine what is the characteristic. Okay. So just till then, you go through this lecture again and again to understand the concept of characteristic well, so that you can understand the theorems which we are going to discuss in our next video. So till then, goodbye and thank you so much.